Hello everyone, my name is Haoyu Wang, the PhD student in University of Virginia, guided by Professor Haiying Shen. And today I will present the paper Reinforcement Learning-Based System for Minimizing Cloud Storage Service Cost. This paper is the collaboration between the University of Virginia and the George Mason University. Nowadays, cloud storage such as Microsoft Azure, Amazon AWS, and Google Cloud Storage has become a popular commercial service provided by cloud service providers. More and more individual customers and enterprises are moving their data workloads to cloud storage in order to save the capital expenditures required for building and maintaining the hardware infrastructures and avoid its complexity and managing the data centers. Cloud storage service can be used by many web applications such as online social networks and web portals, the online banking, airline, ticket booking, and some other electric business web applications. Here is the typical structure of the web application using cloud storage service. A CSP offers different types of storage, including hot, cold, and archive storage, and sets a unit price for these different types, which varies substantially. The payment that a cloud customer makes to the CSP includes the cost of storage, data read, change, and frequencies. Actually, the different storage types has different the pricing policies and different price. We have one example. For the US West in Amazon S3, for the hot storage type, it charges $0.0055 per 1,000 requests and $0.01 per 1,000 requests for the cold storage types. In the US East, for the hot storage types, $0.005 are charged for the hot storage types, and the cold is $0.01 per 1,000 requests. So according to the different price for different storage types, in order to maximize the profit of the application, in other words, in order to minimize the total cloud storage service monetary cost. So we will think about how to minimize the cost. Second, we will introduce the related work. Third, we will introduce the Wikipedia trace analysis. And the next is the Markov decision process problem formulation, which formulates the monetary cost minimization problem into the MDP. Fifth is the main design, and then the performance evaluation. Finally, we will conclude the presentation. Talking about minimize the storage monetary cost, different prices is determined by many features, and we show the three key points here. First is the storage types like the hot, cold, archive, and there are some other features shown in the like S3 website and the Microsoft Azure website. The different storage type provided by the CSP can determine the different unit price. The second thing is the read-write operation frequencies. The different read-write operation frequencies will determine the popularity of one data object, and then the CSP will charge different prices to these different request frequency data files. The third thing is about the storage period. This is related to the size of the data. The CSP will charge different unit prices for the different size of data objects and for different storage period, like per month or per day. So there were several previous work started on the problem or the related problem. First category is the cloud storage payment minimization. Several previous work they proposed several heuristic programming methods to determine the minimum amount of resource needed to satisfy the requirement of web applications, and or to satisfy the storage I/O requirement. The second thing is the cloud resource pricing. Several previous work is studying how to uh, study the cloud resource pricing problem, like how to maximize the benefit of the cloud service customers under dynamic pricing models. The third thing is the combining cloud providers. Several previous work is started the use like combining the different cloud providers together to improve the data availability. Unlike the above previous method, the goal of our method in this paper is to minimize the total payment a cloud storage service customer made to a CSP by leveraging the different storage types provided by the CSP. In order to analyze the study the problem further, we first to analyze the Wikipedia trace, which is widely used in the cloud storage system. The trace include like the hourly Wikipedia page views per article, and in our trace analysis, we take one article as one data, and the whole data is collected from the July 5th to September 5th for about 4 million articles in English. Let's see the first figure. We plot the histogram of daily request frequency standard deviation for all data files in the trace. And we can see that the data files with standard deviations between 0 and 0.1 constitute around 85% of the total number of data files. However, there are still a large number of data files with very high requested frequency variabilities, although they only constitute around like 0.75% of the total number of data files. The rest of data files, which occupy around 50%, have certain request frequency variabilities ranging from 0.1 to 0.8. The next figure shows the potential saved money in dollars versus the standard deviation of daily request frequencies. In order to get the potential saved money, we first compute the total payment charged by the CSP if the customer assigns all data files as either hot or cold, depending on which one is a lower cost. We then apply an offline brute force method on the trace to determine the optimal storage allocation. The optimal saved money is the difference between the two values from the above two methods. The next figure, it shows the 1% and median and 99% of the prediction errors for our data files. We want to use the popular time series prediction model like the ARIMA and use the first 2 months data to predict the daily request frequency within the next 7 days. In other words, the prediction model generates 7 predicted daily request frequency for each data files. We observe that the prediction errors are considerably higher for data files with high request frequency variabilities, which is hard to predict by the prediction method. However, as observed in the last figure, the data files have the most potential for cost savings. Thus, in order to minimize the total cost of cloud storage, it is challenging to identify data files with high standard deviations according to the variable request frequencies to adjust the data storage types. So, considering the challenges, we want to formulate this problem into a typical the Markov decision process. Actually, for one Markov process, it concludes the S denotes the state, A denotes the action, and P denotes the probability between each two states, and R denotes the reward. When an action is taken in a state is transferred to another state with a certain probability, and a corresponding reward is received. So in the state space, we define the state space consists of information on read request frequencies, the data file sizes, write frequencies, and the storage types of the data files. For the action space, we define the action space is here the n is the number of data files under consideration, and AI is action to assign the I isolate files to one data storage type. For example, in this paper, the possible options for one action AI is 3, corresponding to keep the file in the storage types or assign it to either the other 2 storage types, like hard code archive. So the action space will be 3 times n. For the reward, with the main goal of the agent is to make an optimal data type assignment decision at each decision period, like 1 week in our paper. So we define the reward function given an action at the state as follows. So where the CST 80 is the total money cost of taking action 80 at the state ST. The total money cost includes the cost of storage, the cost of changing the storage types, and the cost of read-write operations. Actually, for example, like the storage cost, it is the product of the data size and the unit storage price within each data center, and the read-write cost is the sum of the payment made to the CSP by the read-write operation frequencies. In order to solve the above the MDP problem, we use the A3C algorithm in the in our mini cost we propose, and this A3C is a state-of-art reinforcement learning method involving training 2 DeepQ networks, and the DQN has been successfully used to solve the large-scale reinforcement learning tasks. Here is a typical structure of the A3C, which include the 2 types of DQN, which are actor network and the critic network. And the actor network selects actions according to the probability distribution. The critic network generates the reward depending on the action generated by the actor network. The actor network finally updates the probability distribution according to the reward from the critic network. So, because of the 2 DQN involved in the whole algorithms, the performance of the A3C is better than the typical reinforcement learning method. The next part of the main design is a concurrent requested data files aggregation. For one web application, some data files are usually requested concurrently. For example, different data files they linked to one web page are usually requested concurrently. Based on this key observation, we propose to aggregate 2 or more data files that are often requested concurrently into another data file to reduce the total request frequencies and thus may help decrease the total cost determined by the multiple features and the data files and the storage types. So here is the pseudocode of this method. So first we collect the concurrent request information of all the data files, and for each group of the data files, we first calculate the data file aggregation coefficient, and then sort the group of data files in descending order according to the coefficient. We only select the top 5 groups of data files to generate the aggregated data files. If the omega of the one group of data files is smaller than 0, then we delete the aggregated data files related to this group. So after we use this method, we can somehow to reduce the number of read and write frequencies and keep the same data the size of data transmission, somehow to further to reduce the monetary cost. Here is the performance evaluation, and we use a trace-driven experiment to simulate the environment and to generate the final results. So in the figure 7, it shows the normalized money cost per data file versus the number of days. We see that the cost per data file from using the above algorithm follows the code larger than hot and larger than greedy, larger than mini cost and larger than optimal. The greedy is just use the greedy method to determine the storage type just one day before the uh, data before the decision need to make, and the optimal is offline brute force method, which we can see it's just a lower bound of the lower bound of the total monetary cost for all data files. And actually, we can see that the mini cost can achieve the very closer performance compared to the optimal method. And the figure 8, it shows the monetary cost per data file versus the standard deviation of data request frequencies for all the data files. It shows that especially for the data files with a higher standard deviation, like larger than 0.8, mini cost and optimal can have the much better performances than other methods, and mini cost can achieve the very closer performance with optimal. The next thing we concern is about the overhead of our method. We only show the 4 methods here. This is the computing overhead of each online method for each day. And we didn't show the computing overhead of optimal since it's an offline method which is not comparable to other online method. We can see that the mini cost is kind of similar to the greedy method, so it is okay, especially for that mini cost can achieve much better performance than greedy. The next we compare is the performance with and without data file aggregation. Actually, with and without aggregation, the data performance is very similar, and of course, with the data aggregation, the mini cost can achieve better performance and much closer to the optimal performance, since in optimal there is no data file aggregation. So finally, the conclusion. We analyzed the Wikipedia trees, and to demonstrate that the substantial request frequencies variabilities make it cost inefficient for cloud storage service customer. Second, an RL-based storage types assignment algorithm that generates the storage types assignment plans periodically. And third, the trace-driven experiment to show that our online RL-based method can achieve significant cost savings. Thank you for your hearing, and if there are questions, you can just contact the authors, or you can read our papers. Thank you very much.